Good afternoon and welcome to today's lecture on algorithms and data structures. Last week we finished complexity theory, in particular the omega notation and the theta notation, as well a couple of other smaller things. Then we started with lists. So first of all, we looked at sequences and then into an array, which is a piece of memory we're reserving. And we want to work with an array, but an array has a fixed size. And each element in an array has a certain size. So we don't want to store the elements directly in the array if they have varying size. Rather, we store references in an array and refer to the object somewhere else. So we have the same size per element in the array, which is a memory address. However, the size of the array is fixed, and if we want to increase the size of the array, that doesn't work because we cannot just increase, because the array is somewhere in my RAM, and maybe in the next memory address there's something else. So we need a different concept, and we looked at lists, which we also call dynamic arrays. And in lists, we have an abstraction, and internally we use an array, but we abstract that. And when we need more elements in our list, we create a new underlying array, we copy all the elements in it, and then we delete the old array and refer with that variable to which we use to refer to the low-level array. We switch that and refer to the new array, and the new array has more space. We saw how we can implement this. In the lab, there are a couple of problems on this as well that you have seen. And today, a few students in the lab started working on this and had a couple of questions like, how can we implement a set item, an insert, and delete? You need to think about that and what exceptions may occur. We also wondered about the complexity, which was fairly easy for non-muting behavior, so just reads, for example. But when we write, we noticed we have a problem because an append, in the worst case, may require to resize, but this happens quite rarely when the underlying array is large, because we always want to double its size or its capacity. So we saw that if we always assume the worst case, appending is O of n, but that case actually happens rarely and becomes less or even more rare once the capacity keeps growing, since we keep doubling the capacity when resizing. So we looked at the concept of amortization, and then we say, well, actually appending is O of 1 in an amortized way, and it's still O of n. If you write O of n, that would be correct. If you write O of 1, it would be wrong. So you would need to indicate that your complexity is amortized, for example, with a star, or you write amortized behind, just to highlight that we talk about amortized complexities. This concept was discussed last week, and today we will continue with lists. We have now seen the most fundamental list possible, an array list, which is a list that uses internally an array. Today we will look at a couple of variations of lists. In particular, we'll look into stacks and queues, and then we will look at a totally different concept of lists, which we call a linked list, which does not use an underlying array, but a totally different structure. But in this course, we will talk a lot about different data structures, and I'll introduce a concept now that we call an abstract data type. An abstract data type is a high-level mathematical model of a data structure, and it specifies various parts. For example, which data I'm storing in the abstract data type, the operations that are publicly available, so what I can read, what I can amend, append, whatever. So all the non-mutating as well as the mutating behavior, but only the public interface. And for each of these operations, also the parameters, as well as so what we put in and what we get out from these operations. And with such a high-level abstract data type, we're just specifying what each operation does, but not how it's done. So it's a high-level description of a data structure. And we'll be using this concept of an ADT now throughout this course, and we'll start applying this directly. And then once we have specified an abstract data type, which is just a high-level description of a new data structure, we will try to actually implement the data structure. And then we need to worry about how to do it. But there may be more implementation details that we don't care about in the abstract data type. And now we'll look at a stack. And a stack is something you can imagine like a stack of items you're stacking, or a stack of papers. You have a few operations that you can use on this stack, at least in the simplest stack. You have a stack S, and you can push an item. That means you're just putting something on top. And we're using an item E that we are putting on top of the stack. And that's now the topmost element. I can read the topmost element, so I can use the function or method top, and this one just returns a reference to the top element of the stack, but it doesn't remove it. I can just read it. I can also check if a stack is empty, which returns true or false, and I can get the length of a stack. So I'm just counting how many elements I have in my stack. And then I have one more fundamental method, which is popping. And popping means I'm removing the topmost element and I'm returning it. So I'm not just removing it, but I'm also returning it, which is different to top, because with top, I'm just returning, so reading the topmost element, but I'm not removing it. But with pop, I'm removing it and I'm returning it. So all I can do with the stack is I can put elements on top, and I can remove these elements again from the top. I'm not allowed to read elements somewhere in the stack or to remove them. I can only put elements on top or remove them from the top. Later, we will see that this essential data structure is key to a lot of computer science problems. But before we look at applications, we will see how we can actually implement it. And in order to make this a little bit more concrete for implementation, we'll look at an example. So we have a stack, and initially the stack is empty. And then I'm pushing a 5. So I have a 5 now in the stack. I can push a 3. Now in my stack, I'm storing at the bottom a 5 and a 3 on top. I can also get its length, which is 2. I can pop the stack. That means I only have the 5 left on the stack, and I'm removing and returning the 3. I can check if this stack is empty, which is not the case. I can still pop the 5. Now I get the 5 back, it's removed. Now the stack is empty. So is empty is true. And if I try to pop again, I get an exception, because if the stack is empty, there's nothing I can return or remove. Then I can put again a 7 on top. So I push a 7, I push the 9. I can read the topmost element, which returns 9, but it doesn't remove it. I can push a 4. So now I have at the bottom my 7, then a 9 in the middle, and a 4 on the top, and so forth. So this is an example of how we can use a stack. And we will see now how we can actually implement something like this, which is actually fairly easy using our list that we have used so far, because this is just actually some variation of a list. And what we need is a helper class. I'm defining a helper class, which I call empty, and it's just an exception class that inherits from exception. It doesn't do anything else, but we don't just want to raise an exception or an object of class exception. Rather, we have a more specialized class, empty. So far, we don't implement anything in there. And since we have nothing to put in this block, we just put a pass. But raising an empty exception is probably more understandable than raising the general exception. You're most welcome to customize this class, but that's not necessary for now. Now that we have used or created this helper class, we will start implementing our stack. what I need is my initializer. And internally, I have an attribute that I consider private, and it's just an empty list. I could be using the list that you have implemented, or that we have implemented in the last lecture, our myArray, which was some kind of list, but we don't use that anymore. But we're just using the default Python list, and we're building some interface around it, which is actually fairly easy. What I can do is I can get its length. So what I can return is just the length of my data attribute, because this is a list and a Python list, and I can get a list's length, which I'm returning. Then I can check if it's empty. So is empty. And what I can return is, for example, the length of the data, and I check if it's 0. I could also call the length on itself and check if it's 0, but we're just doing it this way. And now I need my two mutating methods, which is a push. And for push, I'm pushing an element. And since this is a Python list, I can just append an element. Appending means I add an element to the right. We also need to implement the pop. Pop will come at the end. We will now implement top. And for top, I just want to return the rightmost element. I'm not removing it, because index -1 is the rightmost element. I'm returning it. What do you think can go wrong here? Is there something I need to add? If you have any clue, maybe turn on your microphone or send this to the chat or something. If you think we're okay, or if there's anything we should add or take care of. Got a good comment. The stack may be empty. So when you check this, we have our method is empty. We're calling it. And if it's true, then I'm raising my empty exception. And the empty class just inherits from exception. And you can also reuse the initializer then that comes from the superclass. And for the initializer of the superclass, you can just pass a string as a comment. So we can say the stack is empty. Now we're almost done. We only have to implement pop. And again, we need to check if it's empty. If so, we raise the empty exception. And now we do a very simple operation on our list. We can also call pop, because the Python list comes with a method pop, and pop just removes the rightmost element and returns it. So now I have implemented the abstract data type. It's one way how we can implement a stack. Obviously, there are many, many other methods or many other ways we could do this. We could use a low-level array, and we could try to manipulate it. We could use our myArray class that we implemented last time, which was our first kind of list. But then we have to implement like top and pop, maybe or pop at least in a slightly different way. So maybe feel free to do this at home for an exercise. Maybe implement myStack differently so that it has the same behavior. It implements the abstract data type, but maybe use a low-level array in Python or the myArray class, whatever. And we can also see how it works. We call this stack S, and we initialize the object. We can see its length, which is 0. We can push a 4. We can push a 3. We can push a 2. Now we have 3 elements in here. The top element is the 2, because this is the one which is pushed. We can also pop it. So we got the 2 back, and the length is now 2. We can pop again, which is the 3. We can pop the 4. Now the stack is empty. And if I can try to call top on it now, I get an exception because the stack is empty. And popping it will also lead to an exception. So our initial abstract data type was actually fairly easy to implement because we could largely reuse a Python list, which came with all these convenient features like appending, popping, and so forth. If you take a look at our slides, you can also find this implementation in there that I have just shown you. You can also find the implementation of this in my Nextcloud directory where I have uploaded the source file, so you don't copy and paste from the PDF. Always reuse the source files I have uploaded. Now we can wonder about the complexity of this. We can look at the code here, and obviously getting the length is O of 1 because all I'm doing is I'm reading out the length of the list. A Python list, which is O of 1. It's an array list, and we have anyway just counted its length internally, and we'll just read it out from here. Checking if it's empty is also O of 1. Now, what do you think, maybe without looking at the slides, what is the complexity of pushing? If you think you have a clue what it could be, maybe just send it to the chat without looking at the slides, please, because we'll be discussing this in the slides in a moment. So what's the O complexity of pushing? And I want to see some guesses here in the chat, or turn on your microphone. We got a few comments. So if we ignore amortization, then pushing is O of n. Because internally, I'm using my list, and this list calls append. And for append, we know it's O of n because it may have to resize, because the list may be full and it may have to grow. So technically speaking, pushing is O of n. But because I use this list internally, which always doubles when it resizes, we can take advantage of amortization. And so it's actually O of 1 amortized. For example, indicating O of 1 with a star. If you just write O of 1 or 1, it's wrong because it's not constant, but it's O of 1 in an amortized complexity. Top is also fairly easy. Top is O of 1 because I'm checking if it's empty. If it is, I'm raising the exception. Otherwise, I'm just indexing the rightmost element. And since this uses an array internally in the list, it's random access, so it's O of 1. So top is O of 1. And popping, I want to see again your guesses, without looking at the slides, please, what the complexity of popping could be. And any guesses are most welcome here in the chat, or turn on your microphone if you want to discuss with me what you think the complexity of popping could be. Because I'm checking if it's empty. So this is all constant. And one student said it's O of n if resizing. So if I'm popping, I may resize. Maybe for the student who said this, maybe you want to turn on your microphone or tell us a little bit when resizing could come into play when I'm popping, or you want to send more to the chat, but maybe turn on your microphone and let us know why this could lead to resizing.
Because if you just delete something from the stack, so if you have a dynamic array, if you implement it dynamically, it will resize, and so it may be implemented anyways.
And in which way does it resize? Maybe a few more details.
it will have to paste n-1 elements and delete the old stack.
Mm-hmm. But I'm just clarifying, with resizing, you mean shrinking, right?
Yeah.
Okay. So thank you. So everyone, if you use a Python list, we've learned it will resize at some point if it runs out of space and you're adding elements. So there would be just for resizing O of n when you push. But the same effect can happen when you pop. Imagine you have reserved a lot of space and you've had a lot of elements in your list, so you're blocking a lot of space in the RAM, and then you keep popping and popping, and actually most of the capacity you're not using anymore, you're wasting space. So at some threshold, the Python list would also resize and just shrink and copy the elements of the array into a much smaller array. The threshold will not be 50%. The threshold, I don't know, could be maybe 10% or 20%. You don't want it 50%, because otherwise, if you're half full, you're adding, or if you're full, you're adding one element, it will double. You're removing the element again, you would have half the size, and then you would shrink again. So that threshold for shrinking could, I don't know, be something like 10 to 20%, for example, not 50% of the capacity used. So popping could lead to some resizing. So popping would also be O of n, but that case that you resize when you pop is also rare, and actually quite rare. So this worst case O of n is also something that would rarely happen. So we can also use amortization for popping. And we can say for popping, the complexity, yes, it would be O of n, because it may have to copy all the elements in a smaller array to save space. But because that case is so rare, it's O of 1 amortized as well. So by using this amortization, we can just give a much better indication of the complexity. It may be O of n in this very worst case, but that one is so rare. And with these amortized complexities, we can indicate this far better. So O of 1 amortized for pushing and popping, and the others are definitely O of 1, so we don't need amortization here. When you write down complexities, really just use the amortization if needed. So don't just put a star for amortization behind all of those, because that wouldn't make any sense, because top, empty, and length, they have nothing to do with mutating behavior. They're all just readings, or they're non-mutating. And for that, you don't need amortization. Amortization is only relevant for mutating behavior when you have to resize in this context. So this is our stack. And what are stacks actually useful for? Stacks are used internally in your operating system when you execute function calls. So you're calling a function, and in your current context, you have various local variables, you have register values in your CPU and other things, and you need to store them, because when you open a new function, you would have a new local context, plus you would have maybe new variables in the registers of your CPU, plus other things. So you need to store that somewhere when you're calling a function call, so you're able to go back to your current function call once the one you're calling has actually terminated. And an operating system internally uses a stack for that. So when you're doing a function call, you're just putting something else on the stack. And then once your function call finishes, you're popping and you're putting your values back in your local context, as well as in your registers on the CPU, plus a couple of other things. So whenever you have function calls, your CPU internally will use a stack to handle all of this. Or your operating system is using a stack for this. Then maybe if you want to reverse data, you could just use a stack. Imagine you have values 1 to 10 in that order, 1, 2, 3, 4, 5, up to 10. You could put first a 1 on a stack, then a 2, then a 3, then a 4, and up to the 10. And then you would start popping again, and you would pop the 10, then the 9, and so forth. So like this, you can just reverse the order of your data set. Maybe not a very efficient way, but a stack could be used for this. When you work with, for example, the front end of a compiler or something like this, for that, a stack can be very helpful, because if you have an early stage of a compiler or something that is part of a compiler in the early stages, you need to check, for example, if blocks match or parentheses, because with a parenthesis, you're opening a block, later you're closing it, or with a curly brace, that's what you use, for example, in C++ or Java to open a block, but you're opening some new context with parentheses, and later you want to close them, and you want to check if they are opening and closing in the right order. And this is something that can be solved very well with a stack, because you're pushing stuff, and then for openings, or you're putting those three in that order, and then a closing bracket is coming. And when a closing element is coming, you would be popping from the stack, and you would then check if the one you're popping, which is this opening bracket, would match the closing one, and this is a closing one, so this would match. However, if you first put a closing curly brace and you have a bracket, an opening one on your stack, that would not match, and you would throw some kind of error in a compiler or syntax checker, whatever. Also, if you have a markup language like XML or HTML, you have blocks or that are opening, then closing instructions, and you would also, with a stack, process this and make sure that the ones that are opening are being matched in the right order by closing ones. So there are plenty of applications for stacks. In the coursework, you also find some work on stacks to get some more practice and see what to use them for. So give a try at the coursework, and you'll get a better understanding, and you'll see various applications of this fundamental data structure. But internally, it's just some kind of list, the way we have implemented it, but with a slightly different interface, because we can just push and pop and get its length and the topmost element and see if it's empty. These are stacks, and we will now implement a different abstract data type, which is also a type of list. It's a queue. A queue, again, we will look at its abstract data types, and a queue works quite different to a stack. So I have a queue that I call queue, and it has two mutating methods. One is enqueue, and enqueue means I'm adding an element to the back of the queue, so the end of the queue. For example, to the right of the queue. If I dequeue, I take and remove and return the first element from the queue, so from the left end. So with a queue means I'm adding something to the right and I'm removing from the left. And there's also this expression of first in, first out. First in, first out would be something that refers to a stack, because first in, first out refers to a queue, because the element you have put in first on the right would be the one that would be the leftmost element, and that's the first one you're removing. A stack works different, because with a stack you're putting elements on, and the last one you put on the stack is the one you would be taking out first. So a stack would be last in, first out, like LIFO, and a queue would be first in, first out, which is FIFO. So these are sometimes abbreviations that you would see: last in, first out, or first in, first out, whatever. So these are the mutating methods. But we have a few more methods, like, for example, we want to read out the first element, meaning we read out the leftmost element without removing it. We can also check if a queue is empty, and we can get a length of the queue. And now we will try to implement this again. And I'll show you how, and we will run actually in a couple of challenges because this will be more complex. But I think before we implement it, there's one more slide I can discuss with you. And with this slide, we'll just see an example of how this works. So we have an empty queue and we enqueue the 5. So we put in the 5, which is the leftmost element, the first element, but also the last element, because there's only one element in. I'm enqueuing a 3, so I'm putting the 3 to the right. Now I can get the length, which is 2. I can dequeue the 5. So I'm getting the 5 out, the leftmost element. Now I only have the 3 left. I can check if this is empty, which is false, because there's one element left. I can remove the element by calling dequeue. Now the list is empty. I can check if it's empty, which is true. If I call dequeue again, I get an error. I can enqueue a 7. Then I can enqueue a 9. I can also call first, which is just reading the leftmost element. I can enqueue again a 4. So I have 7, 9, and 4 in it, and so forth. So this is one example of how a queue works. We will first of all implement queues again, and then see a couple of applications of queues in computer science. It's again a fundamental data structure. For example, schedulers in your operating system use some kind of queue, but we'll look into the applications in a couple of minutes once we have actually implemented this. And I will open my coding environment and screen share it with you. So we are writing a class, and again, we need our empty class. So just for the exception, empty, it inherits from exception, and it's just a pass as before. This one is now not repeated in the slides, because in the slides we've only done this once. But when I raise an empty exception later, you can just add this in your own implementation, so you have the empty class. Now we will implement our myQueue, and myQueue has again an initializer, and the initializer will now create 3 attributes. One is size. So initially there are 0 elements in my queue. I also need a list that I'm using internally. And the list that I'm using is, I will say that my queue has a fixed capacity initially. And we don't just want to start with one element, because if I add a second element, I need to resize. So rather, I'm reserving some space, and I'm putting all none values in the queue. So a none is just a null pointer. And I say, well, this times some default capacity. So say by default, my data attribute refers to a list that has size 10 and only contains none references. We will later see why we need these none references. We can also slightly differently customize this. In the slides, I call this a default capacity. And I'm putting the default capacity here outside the initializer. This is something that you would call a static attribute, so one that has a class context. It's not an attribute from the object, but rather from the class. And I can also refer it to it by saying myQueue. Hope I spelled it correctly. And like this. And like this, I refer to something that has class context. We need another helper variable that I call the front, and front is an index. And we will see in a second why this is, or what it's useful for, because I will visualize this on the iPad. But before we do this, we already add a couple of helper methods. For example, we want to read out the size or the length of our data structure. So I'm just reading out size. Size is a counter, will be increasing later when we enqueue elements, and we'll be reducing it when we dequeue elements. And we can also check if it's empty. And we check if it's 0. Now I have done this one here, and I said, well, I'm creating a list of, say, 10 elements that all have none references. Why am I doing this? It looks unnecessarily complicated because I could also just be, and I'm putting this in a comment, I could say, well, the data is just an empty list, and later I'm enqueuing and I'm dequeuing. And we could imagine how we could implement such a method, which is not what we are doing in the slides, but I'll show you now a very simplified way of how we could implement theoretically our MyQueue. We can have the enqueue method, and we could say something like, well, what I want is I'm going to take my data and I'm going to append the element E to the right. And I'm also increasing the size by 1. And appending takes care of resizing the list if necessary. So assuming I had implemented a list like I have done up here in the comment, but this is something we won't be doing. We could also then think about our dequeue. And dequeue could be implemented something like this. I'm avoiding now the exception, so the exception handling will come later. Or we can already do it now, actually, in fact, and it's done. So we can say if it's empty, I'm going to raise an empty exception. And I say queue is empty. And how can I pop the leftmost element of a Python list? Does anyone remember this? When we looked at graphs, we implemented this highly generic graph algorithm, and we were able to remove and return the leftmost element from the frontier. If you still remember how this can be done, maybe send it to the chat. Or send me maybe a thumbs up if you still remember how this could be done, or a thumbs down if you have no clue anymore. And we got the right answer. We could say self.data, and we pop element 0. Because if you call pop, this removes the rightmost element. And I can put in a different index like 0. And 0, pop 0, would be removing the leftmost element. However, this comes with lots of problems. Because if I use internally an array in this Python list, and I can only efficiently pop the rightmost element, because I have my array and I just, remove the rightmost element and I change the size by 1 or something like this, and I'm done. But if I pop something in between, or the leftmost element, actually, I cannot just remove this or have it unused. In fact, I need to create a new array internally and copy everything except that one element. I will visualize this now for you. And here I'm writing something like not good. And we will later see how we can do this in a different way. I'll switch now to the whiteboard. So we will have now, say, lists and we have the pop method. If we have a Python list that looks something like this, I have all these elements, and I have elements, say, A, B, C, D, and E, and an F, and I call pop. What happens is I'm eliminating the F and I return it. So this returns F and has eliminated. And all I'm doing is I'm changing the size, because the size was before 6. And then when I pop, the size becomes 5. And I can append again. And when I append again, I just put it there again. Fairly easy if I do a regular pop. But I can do this in a different way. And I can write something like this. And I pop at 0. What would happen is I'm removing this A, and yes, I'm updating the size, but then I now have an empty element, not at the end of the array, but at the beginning of the array. Or if I do a pop 1, it would be the B, for example. And then I have holes within my array, and my array structure and how I'm building the lists don't really handle this, because I would then keep a list of, or keep track of, which elements are actually in between empty, and this would all lead to lots of inefficiencies. So if I call a pop 0, what happens in a Python list is something like this. If I call pop 0, I'm actually creating a new array, and I'm copying all the elements over. So I'm copying the B in here, C, D, E, and F. This would happen at a pop 0. And obviously the pop 0 would return me my A. And then I would create a new array and copy just to avoid holes in an array. And if I do this, I have a big problem, because the complexity of this is theta of n. So guaranteed to take something in the order of n, because if I remove something in between or at the left, I need to copy everything else. So pop only has a complexity of O of 1 in an amortized way if I pop the rightmost element. And by default, if I don't put a parameter, it pops the rightmost element, and it's O of 1 amortized. It's amortized because popping could internally lead to a resizing that I need to copy into a smaller array, but we're ignoring this for now. So O of 1 or O of 1 amortized if we take resizing into account, but all the other pops with a different index is guaranteed to take theta of n. So going back to how we wanted to implement our queue, if I do a dequeue and I pop the leftmost element, which removes and returns it, this takes theta of n. I'm writing this theta of n. And this is really not great, because each time I'm dequeuing, I have a theta of n. So I'm unable to build my list, my queue this way. I need something completely different to build an efficient queue. And that's why I'm not creating my queue like this, but rather I'm creating a queue with none values, and I'm actually building the queue in the form of a so-called circular array. And this is a concept I will explain you now on the whiteboard again, and why it's highly efficient. And once we have described this on the whiteboard, how a circular array works, we'll be looking at how we can implement it in detail. It's a little bit more complex than what we have done so far, but it will lead to a highly efficient data structure. And I'll show you now the concept of a circular queue. Or, well, not a circular queue, we call it a circular array. It's better because we're using a circular array to build a queue. What I have is initially my list, which contains all these none values. That's what we have built before in the initializer. But for now, I don't put in the none values. They are in there, but I don't write none because we just imagine that all these empty spots include a none, which is just a null pointer. And we have our initial size. Our initial size is 0, and the initial capacity would be here. Indexes 0, 1, 2, 3, 4, 5, 6, 7. So we have a capacity of 8 elements. Capacity is 8, and the size is 0. Now, I'll explain the concept of a circular array. If I enqueue something, in the first case, and we have before another variable that I call front. You remember this? I said there is another variable that we created in the initializer that we called front, and front was initially 0. And the front initially refers by 0 to index 0. If I enqueue something now, I will just put the first element, say an A, in here. If I enqueue the next element, I will put it in the next index. Meanwhile, the size, or just put it step by step, the size is 1 now because we have an A in. And if I want to put the next element in, I need to calculate an index. And that index is calculated where I'm putting the next element by adding size and front. And adding size and front gives me 1. So I'm putting the next element in here. Then the size is 2. The next element in here. Then the size is 3. If I put in another element, it would be then index 3. So this is enqueuing. But I can also dequeue. And if I dequeue, I actually have to do something different. If I dequeue, what I want is I remove the A and return it. And I'm changing the size to 2, but I'm moving the front by 1. So the front will now refer to index 1, not to index 0 anymore. I can keep doing this, and I'm now not keeping track of the size anymore for now. So we're just adding more elements. We're adding a D, an E, an F, a G, and an H. We have a capacity of 8. Now we have a size of 7 once this is done. And if I want to add or enqueue one more element, I need to imagine this as a circular array. So the last element is connected to the first element. And then actually, I can still enqueue something in here, which I would call now an X. Now my circular array is actually full. So if I add now another element, I need to resize, but I'm not doing that now. So the size would be 8. If I do a dequeue again, this B would be removed and the front index would refer now to the C. And the size would be 7. So with this circular array, I have one big advantage. Enqueuing, yes, for enqueuing, there's not much of a difference to using a regular list in terms of the complexity. But for dequeuing, I can very efficiently dequeue because I don't need to call a pop 0. Rather, I'm just looking at what a front index looks at. I'm removing and returning that element, and I'm changing the front index by 1. Is this something you feel looks reasonable to you? So did you get the idea of a circular array? Maybe thumbs up, thumbs down if you agree to this idea I have shown. Good. I will now discuss with you how to implement this in Python. And it's actually not that difficult. It requires a little bit more maths and thinking about the circle, but it's actually fairly doable. We already have implemented the front index. Now you know what it's for. It refers initially to the front, which is 0, and later the front index may change. The size is 0, and we have our list of an initial capacity, and they're all none values. So later when we pop something, we just put maybe, for example, a none value in there. So not pop, I meant dequeue. When we dequeue, we return that element, and in that slot, we put a none value. We can try to implement this now. So we also need another method that so far I have skipped. One method is a helper method to read that we call first, and we said first is the leftmost element in the queue. First of all, we need to check if the queue is empty, because if the queue is empty, we again need to raise an exception, because if something is empty, we cannot peek at the first element. But then we can return index 0 of data in the first case, because this is the leftmost element. But now it's a circular array, so I need to put something different than the 0 in here. Maybe for you, without looking at the slides, what do I need to put in as an index rather than the 0? So which variable refers to the first or leftmost element in my circular queue, circular array, so the element that I actually want to look at. That's correct. That what you wrote itself dot front, because front always refers to the front, and later the front will change when we enqueue or when we dequeue. But this is something we'll be doing now. So front is initially 0, but later front may refer to a different index. When I dequeue, I need to, first of all, check if I'm empty, and if that's the case, I raise an exception. I want now an answer, so the value I'm going to return, and I just need to repeat what I have done for first. So I'm just going to take a look at where the front refers to, and I'm going to return that. And there are a few steps in between. If I dequeue, I need to update the size, because the size goes down. And now there are two pieces that are a little bit more tricky. I said I removed that element because I'm going to remove it from the queue. And in my circular array, where I use the none reference for entries where I have no value in. So I'm going to say data at index front is none. Because I have my answer, I'm going to return it. And I'm overwriting where the front is with a none reference. And I can update the front, and I can add one index on top of the front, because the front will be moved to the right. Do you agree with this implementation, or is there something that could be going wrong? If you feel this implementation is a good guess, maybe thumbs up. If you have concerns with this, thumbs down. And I guess the way I'm asking, it's quite obvious there's something wrong. And for the ones of you who think it doesn't work, maybe turn on your microphone and share with us what could be going wrong when I implement it like this. Or send it in the chat.
When you when you dequeue something, you get a few holes in your queue, and when you proceed and enqueue something again, you quickly get to the limit of the list and have a few entries that are not processed anymore because you have holes in it.
Okay, we want to avoid the holes, but enqueuing is something we're doing later. Or which line do you think is the problematic one then in my code? Fine, I will explain this now. I'll show there's only one line that is so far a problem. There was a student saying adding these none or putting these none values at an index. That's totally fine, because with a none value, we indicate there is no value in there. So we don't really create holes. Because when we dequeue, we just put a none reference in just to say, well, there's really nothing in it. We have the following problem. Imagine, so we're ignoring now the size. Imagine, and one student said this now, if I just keep dequeuing and dequeuing, I keep moving the front to over here. And now, well, I have still my age. I'm dequeuing the age. And then if I update the front again, +1, it would be referring here. And two students got this, or three students got this right. The front would be wrong. So rather than adding +1, the front finally needs to refer to here, because the front will otherwise be an invalid index. And this is the only line that was wrong, or not fully correct yet in our code. And what I'm doing is I'm changing the front. I'm saying, well, I'm adding 1 on top of the front, but I need to take a modulo operation, and I take this modulo the length of my list, because my list has a certain length. Initially it's 10, later it may resize and grow, it could be 20. And when I add +1 on the front, at one point it could be an invalid index. And that's why I need to take modulo the capacity. And like this, I make sure that, say, my invalid index would be 10 at some point, but 10 would be invalid. So that we could say, for example, my greatest index is a 9 + 1 would be 10, but 10 is an invalid index, but the capacity is 10 because we have the indexes 0 to 9. So I take the 10 modulo 10, which is a 0, and then I have the valid index 0. So this is what I had visualized, and now you also see how to compute it, because I add 1 on top, and then I take the modulo. And this is something we also need to look at enqueuing, because the same can happen with enqueuing. So enqueuing, again, is, there are a few parts in enqueuing that are fairly simple. I am adding an element, and I have an index that I call available. And in the index available, I'm putting my element E. And the index available can be computed because we always said before, we take the front and add the size on top of it. This is something I had visualized before, and I said this in the very beginning when I visualized the circular array. We say front was 0 and the size was 0, so that was index 0. But when the size was 1, I wanted to put the element then into 1. And actually, the general equation is the next index where I'm putting the element is I take the front index plus the size. Initially, both is 0, but later the front keeps moving and the size keeps changing. So available would be self plus front. And here, the same problem can happen if I have a large front value. Maybe say the front is one of the last few indexes, but I have a certain size. I also need to take into account that this is circulating, and I need to go again to the beginning of the circular array in order to put the element there. So again, I need to take self.front plus self.size, and I take a modulo of the capacity. And it's just the same equation more or less like here. Well, there I said front plus 1, now front plus size, but I take modulo the capacity. And like this, I'm able to actually build this in a circular way. What other problem do you see with enqueuing? Something can still go wrong. If you have an idea, maybe thumbs up or turn on your microphone. It's not the indexes, it's something far more fundamental that can go wrong when enqueuing. Someone says we want to check if it could happen that we overwrite. Yes. So actually, we need to check that we're not running out of space. So we need to check if the size is actually the capacity, and the capacity is the length of the data, and with our size. And if this is the case, I also need to resize because I just don't have space anymore. And if I keep enqueuing here, I will just overwrite. And that's what I also don't want. Maybe in some kind of buffer, you want to do this, but this is not a buffer, it's a queue. And here we don't just want to override. So I need a new helper method, which I call resize. And resizing is, I'm just taking the capacity times 2. And resizing is actually, turns out now, the last method we need to implement. We have a certain capacity. And what I need is, I say, well, this is my old data, because I'm now creating a new underlying list with that is bigger. So I'm calling this old, and my data now refers to a new list, which are all so far, which are all just non-references, and I have capacity many. Capacity would be for enqueuing bigger, so we have more. And now somehow I need to copy from the old one into the new one. And I think I will visualize this again, how this works. Because this may be a little bit tricky, but it will also actually be fairly easy when we try to visualize it. So we call this resize. And say we have something like this, 5 elements. We have an A, B, C, D, E. The front, for example, refers to here. And we have 5 of them. And now I want to enqueue. And actually enqueuing would be front. So the front is, and I'm just adding the indexes. something like this. And I'm just, so front is 1 and size. And before we saw front and size, we add them together, it's 6. So I write NQ 1 plus 6, 1 plus 5 modulo 5, because 5 is the capacity. So this would be 6 modulo 5 is 1. That means NQing would actually write into here. That's exactly what we don't want. So we need to resize. And resizing is now a bigger array of some size, for example, 2, 4, 6, 8 in this example here. And could be 10 the way we have implemented it. And there's one student here who wrote me some comments about the code. We will look at the code in a moment and the problems you have raised. We will anyway try this in a moment. But then we'll look at the code. So I'll explain this first. Now, when I copy, so resizing means I have now my new array or my new list, and in there I'm going to copy. And I have my front that I will later overwrite. But first, I'm starting at 0, and I'm writing the indexes. And by convenience, I will just put the A into index 0, the B into index 1, C, and D. And then, again, I need the circular approach to continue copying the E into here. And then, in this case, I'm actually done, and I have space for a few more elements. So what I've just done is I've created a new list, and I'm copying from the old one into this new list. And then this new list, eventually, once it's done, I also need to update the front, which refers to 0. So when I have resized and I have copied, I actually have a clean state because index 0 is the front, and then I have all the elements in, and these last ones, I have the non-references in. It is not circular at that moment, but if I have enough NQs and DEQs, it will become circular again. So one student wrote me, he or she says that I forgot the underscore before data. You're right. This is here. So anyway, later when we run it, there may be some bug in it, and we see if it works in the first attempt or not. In the slides, it's correct, as well as in the helper file with all the code. And you say I defined NQ 2 times. That's correct. So there's this old NQ up here that use this appending whatever, and we increase the size, but this was the old NQ that we don't need anymore because we're not just using a list, we're using a circular array. Now it's cleaned up. Hope these are the 2 points you addressed. And for resizing, we will do now the following. We have our new data, and we're going to create a helper variable now, which is called walk. And walk starts at the front index. And I'm going through actually a second, or I'm going through a loop now, and I have an index in the loop, which I call K. And K is in the range of size. And so it starts with 0, then 1, and so forth, up to size, where size is not included. And the data is at index K, because initially this will be just index 0 in the data. And I'm taking the walk, and walk is where the front referred to. So this was the example I'd shown on the iPad, that the front refers, for example, to index 1 or index whatever. And I'm starting from there, and I'm copying into index k. And k is 0. And then I have done this, and I need to update my walk. And I cannot just add 1 on top of walk, because at some point I'm at the end of the queue, and I need to take advantage of this, or not the end of the queue, the end of the array. And I need to take advantage of this circular array. So I'm adding 1 on top of the walk, but I need to take this modulo the length of old. And old was my old underlying array or list or whatever. At some point it's copied, and the last thing I need to do is I'm updating front to index 0, because the first element in the queue will be now at index 0. This is what I had visualized. And now we have built a queue, and we can test it. So we're creating an instance of the myQueue. And initially, we see the queue has 0 elements. Queue is empty. That's true. And now we can enqueue. For example, 2. We can enqueue a 3. We can enqueue 6. The length of this is 3. Queue is not empty anymore, and we can dequeue. We get the 2, and now we see we have 2 elements in it, and we can enqueue more elements. We can enqueue a 1, a 2, a 5, a 7, 9, and a 10. We have now the length, which has 8 elements. We can enqueue a 20. We can enqueue a 40. And there's one student who says he thinks that overwriting would be possible. He thinks overwriting is possible with the enqueue function if no element is dequeued before the list is full. I think it totally works, but feel free to debug it. And if you think there is something that doesn't work, let me know. But I've tested it quite many times in the last few years. It works, because eventually this is highly generic. I'm checking if I run out of space. I'm resizing. The walk may be 0 or not. And in this loop, I'm copying it correctly. Then we have 10 elements in it. We can also dequeue. Now we have 9 elements in it. We can also try to peek into the data. Something it's private, but we can still do it. It looks like this. And we can, for example, enqueue another 40. Looks like this. And then we can enqueue again, say a 99. And then it resizes. And as we see, it's actually all copied correctly. Feel free to debug this and understand it in detail, but I know it isn't that easy because we need to take care of these modulus. But overall, this circular array is highly efficient compared to if we use the pop0 in the dequeue. What I have shown you is available in the slides. And in addition to the slides, you also have this zip file where I have all the code examples in it. If we briefly look at the complexity, yes, obviously first empty and length is O of 1 because they are just constant. Enqueuing is O of 1 amortized because, yes, enqueuing, the worst case could be O of n for resizing, which is rare. That's why amortized O of 1. And with dequeue, it's O of 1 amortized. It's not just O of 1 because it's amortized because it could be O of n because if it resizes and shrinks. This is something we have not done in here in exactly this implementation. You could amend our implementation with dequeue and you say, for example, if I dequeue and after dequeuing, I just use less than, say, 15 or 20% of the capacity, I'm resizing in a newer array that is smaller. You could be doing that, and then it would be O of 1 amortized. The one we had looked at strictly is O of 1 because we don't have any resize in the dequeuing. But if you make the dequeuing a little bit more smarter so that it doesn't waste space, then if you do it right, it would be O of 1 amortized. If we didn't use our circular array, then this dequeuing would be actually theta of n because we would be calling pop0, and pop0 is theta of n, and that's really bad. When we discussed these highly generic graph algorithms a few weeks ago, we used a pop0, and at that time I said in a lecture, a pop0 is not that great. Maybe you remember that. It was a small node at that time. Now you know why. You could be rethinking about how we could improve our generic state space search, the shortest path and the lowest cost. Maybe we wouldn't be using a list, but rather a queue in order to handle the frontier. And then we could be using something like this for efficient enqueuing and dequeuing. So this is also something I think I asked a few times in the exam, how you would actually change the shortest path algorithm. And the solution was we're not using a list for the frontier, but rather a queue to take advantage of that, because a pop0 is really not great. Where do we need queues for? Queues are helpful for scheduling. So it's used in your operating system because you have threads and processes. They get a time slice once you interrupt them or you don't give them time anymore. You enqueue them to a queue, and then the scheduler dequeues something. So all the processes and threads are managed in one or multiple queues. Input-output buffers are also a classic example for queues. You put in something, and the element you put in at the beginning is the one you're dequeuing. If you look into the literature, there are so-called double-ended queues, and double-ended queues means it's a queue, but from both sides you can add and delete if you want. So the abstract data type would be we can add a first element, we can add a last element. So this would be our enqueue from before. At last, at first would mean you add an element to the very left. You can delete from both sides. Plus, you can read out the first, last element. You can check if it's empty, what's its length. This is proposed in the literature, but I think this is largely theoretical. I haven't seen many really useful applications for a double-ended queue. But if you ever hear about a double-ended queue in short DEC, that's what you need. But feel free to implement this on your own. You can easily implement it with the tools you have learned so far, but I don't think this has much really useful applications. There's an example here that you can study on your own that you can add to the left and right. But again, I don't think this is used much. Now, today we have discussed stacks and queues, and we still have a little bit of time to look into a totally different approach for lists. The lists we have built so far internally, they are array lists. They use an array, and this array either has to grow or shrink, and at some point, and such an array list allows us to keep elements in a certain order. Linked lists also allow us to do this, but in a totally different style. And in a linked list, we actually have a list that is not built from an array, but actually from lightweight objects that we call nodes. So it's an object-oriented approach. And each node maintains the reference to its element, so the actual element that is stored, as well as, in the simplest case, a reference to the next object. So you have a head in your list, in your linked list. The head refers to the first object. The object contains a reference to the value that is stored in it. And then that object contains also a reference to the next object. And that next object contains, again, a reference to the value plus a reference to the next object. So this is a totally different approach. And these linked lists where you have a list that only refers to a value and the next object, that's called a singly linked list. So it looks like we have the head, it refers to this object. The object refers to some value, whatever it is, and has a reference to the next object and so forth. Then sometimes you have another attribute that you call tail, and tail refers to the last object, and the last object does not have a reference to its successor because it is the last object, and for that you just have a null pointer or a none reference in Python. And these lists, we'll see today how they work. Next week we will start implementing them. And next week, we will also compare them to the array-based lists because both approaches have their pros and cons. We can think about multiple operations. Say, this is our initial singly linked list. We have a head, we have these objects. What we can easily do with a linked list is we can insert an element at the head. So I'm just creating a new object, which my newest object, and I say, well, it refers to a successor, and the successor is the element where the head actually referred to before. So that's just a memory reference. Now the new front or the new head refers to the old head, and the head reference in my linked list object refers to the new element. So this is something that I cannot do that efficiently in an array list, because in an array or array-based list, I can only easily append at the end, but not at the front, because if I want to add something somewhere in between or at the front, I need to create a new array and copy. And that's exactly super inefficient about array-based lists. With these linked lists, I can just go to the head, create a new object, plug it in so that it refers to the old head, and the new or the head attribute refers to a new object. So adding something here is super easy at the front. At the tail, it's also efficient because I have this tail reference and I said, well, this last element doesn't have a successor. Now I create the newest object. The old tail now refers to this newest object. It's the last element, which one doesn't have a successor. And the tail is an attribute of the singly linked list. It refers then to this new object. So I see with such a linked list, I can very easily add new elements at both ends, at the front and at the end. Since we still have a little bit of time, we can actually already get started and see how we could implement something like this. I will screen share this now. I say I have a class that I call linked stack. I'm now building a stack based on top of a singly linked list. So a stack you learned today, I push and I pop. And today we're building now a stack that is not based on an array list, but based on a linked list. And I need an initializer. And the stack only needs two attributes. It's a head that refers to none initially because there is no head. So head is always the topmost element of the stack. And I have a size, and the size is 0. I can try to read out the length of this. It's fairly easy because I'm just returning the size. I can also wonder if it's empty. If it's empty, I am checking if the size is 0. So far, not much of a difference. But now we'll actually introduce a bigger difference, because I said our stack this time is not based on some array list, but based on nodes, and nodes are used to build a linked list. Something you can do in Python, but also in some other programming languages, you can create a class or define a class within a class. And so we have a subclass node, and this subclass, no, sorry, it's not a subclass, it's an inner class. So this has nothing to do with inheritance, because subclass would mean inheritance. It's an inner class. So it's a class within the class linked stack. And we call it node. And since we want to indicate it private, that it's only used by the linked stack class, we put an underscore in front of it. And this also needs an initializer. And well, today, lots of typos, I'm sorry. So what I'm creating is a node object, and the node object contains some element or a reference. So this is the value stored in there. It can be an integer, can be a reference to whatever object. And I also have a reference next. And next will then be an attribute that refers to next. What we use this for exactly is something we'll see in a moment. You're maybe wondering, why is next in green? Next is actually something that is used in Python for iterators. So ideally, we don't call it next. We call it next element, because otherwise we override the next, which is a helper for iterators. Iterators is something you'll see later in this course. If you look in the slides, it's called next. Here we just call it next element to make it more obvious what we mean. Now I have a few methods left that I can implement. Let's start with top. Top reads out the top of the stack. And what I'm returning is I'm going to self, and the head later will always refer to the topmost element of the stack. And I'm reading out its element value. So self._head refers to here, and head will later refer to an object of class _node, and those have an element when they are initialized. We'll later see how to initialize them. What can happen again is that this is empty. If it's empty, we're going to raise an empty exception. So stack is empty. Later again, we need to define the class empty. If I forget this, maybe just remind me. And now we can also try to push something on the stack. I push an element on the stack. So I'm increasing the size +1. And what I'm doing is I'm overriding, or I'm assigning a new value to the head reference. I am creating a new node object. So self.node, and I open parenthesis, I'm creating an object of the node class. I'm passing my element E, whatever it is. And next refers to the element under it, because I'm pushing now something on top of the stack, and my head refers to the topmost element. And later, if I want to remove the topmost element, somehow I must be able to go back to the element below. Now it's not an array list anymore, but rather my top element, which is a node object, refers to the one under it. And the one under it is the one that was the head so far. So head refers to some element. I'm creating a new node that refers to the current head, and the reference to this node is where the head now refers to. And what I have stored here is a memory address to the object under it. And then we're almost done. We can also pop. And again, we need to check if all of this is empty. And if it's empty, we raise an exception. Otherwise, we're going to do something. We will now look, so pop will not return an object, or not an object of class node, but rather pop will return this element that we have stored in here. So it will do something like this: self.head.element. It will return the element. I need to update the size. And return res, but I have now one piece missing. I need to update the head reference, because now I've reduced the size. I have my topmost element value, and that's the one I want to return. But I also need to make sure the head now refers to the element under. And the element under was something like, well, the head now refers to actually its next element. And up here, we call this underscore next. We will call it maybe also next element and something like this. So in the slides, we just call this next. Here we call it next element. So we are updating the head reference by the reference to which the head node referred to under it. I don't need to take care of garbage collection. All of this is done for me. And we will quickly test it. And next week, we'll discuss it further. So I create an object. I say L is a linked list or list stack. And then I can push a 1. I can push a 2. I can push a 3. And then I can pop, which gives me the 3, the 2. The length of the structure is now 1. I can push again a 100. I can pop the 100. I still have one element left, which was this 1 from before. And if I pop again, I get an exception. Here, actually, I should have defined class empty, which I forgot. I talked about it before, and then I forgot it. We obviously need class empty, but what we actually see here from the stack trace, it's trying to raise an empty exception, but it doesn't find class empty because we didn't define it, because I had restarted my IPython session. But how to define class empty as an exception subclass is something we saw. But it will raise eventually the exception because the linked stack is empty. So we have seen now a completely different approach how to build a stack. This approach is also in the slides. In the slides, there's only one tiny thing for this node class. I have defined this underscore slots underscore. This only helps us that the memory footprint of these node objects is a little bit less, but this doesn't matter for this course. And we've now seen a totally different approach how to build linked or lists or stacks, because they are now not using an array, but they are using a node structure, and these nodes are interconnected. Here for a list, for a stack, we have implemented it. In the next week's lecture, we will continue with linked lists. We'll see what they are useful for. We'll discuss some of their complexities, and we'll compare them to our array-based structures, because both approaches have pros and cons. And then next week, we'll also be able to start looking into recursion. Recursion is a concept that an approach that allows us to solve certain computational problems in a very different way, and it allows us to do divide and conquer very easy. If there are any questions, maybe just send them quickly now in the chat, or maybe raise your hand here in the participant section, so I see if you raise your hand or not. Next week, again, we'll continue with the linked lists. We will see a few more details and compare them to array-based lists and a couple of applications. And it's important that you're familiar with Python at this stage now in the course, also with object orientation, and then you're able to take full advantage of the coursework. And I guess you can finish nearly all the coursework now about lists. Next week, we'll finish a little tiny piece of linked lists, and then we'll continue with recursion. I wish you a good weekend, and I look forward to seeing you next week in a lab and in a lecture. Take care. Goodbye.